All right, next up we have the valence bond or VB theory. This theory has to do with formation of something called hybrid orbitals. Or the hybridization of the central atom, how the central atom is able to accommodate 2 or 3 or 4 or 5 or 6 electron groups. So it says in letter A, when bonds form in a molecule, or this could be in a polyatomic ion as well, the orbitals often overlap. We're talking about the atomic orbitals. The s, p, and sometimes the d atomic orbitals mix to make new orbitals with a larger lobe on one side of the nucleus. Now, this larger lobe allows for more effective orbital overlap and stronger, more stable bonds. The angles that these hybrid orbitals take match the angles described in the VSEPR theory. Consequently, these two theories complement each other and work together and help us better understand molecular bonding and geometry. So we're going to be looking side by side at the VB theory and the VSEPR theory. And so that's what we're going to do. We're going to compare those and see how, again, the central atom can accommodate so many electron groups. There's a table on page 293. It shows how the different hybrid orbitals form and then the geometry around the central atom based on those hybrid orbitals. So we're going to kind of do something similar as to what's shown there in the table and what's shown in the book on the subsequent pages. So let's do this. Let's take a look at BeCl2. We'll start with the Lewis structure, and then I want to show you the atomic orbitals in beryllium and see how they can be used to form two covalent bonds. So something that's really important to understand is that in order for an atom to form a covalent bond with another atom, it needs a half-filled orbital. So how covalent bonds form is that two half-filled orbitals in two atoms overlap, and then those atoms share then that pair of electrons. So we see the atomic orbitals of beryllium. I showed the 2p orbitals there for a reason. We'll see why in just a second. And I showed them drawn up higher, indicating that the 2p orbitals have more energy than the 2s orbital. It doesn't make that big of a difference in what we're doing here, but I just wanted to show that nonetheless. So again, in this molecule, beryllium needs to be able to form two covalent bonds. So in order to do that, how many half-filled orbitals does beryllium need to form? It needs to form two half-filled orbitals. How many of its atomic orbitals need to combine to form two half-filled orbitals? The answer is 2. You'll see this pattern throughout all of our examples. So here's what happens. Beryllium's atomic orbitals, 1, 2s, and one of its 2p orbitals combine to form two new hybrid orbitals called sp hybrid orbitals. I tried to show, though it's not that big of a deal, that the two new sp hybrid orbitals, they're called, have energy in between kind of those of the 2s and 2p. And so let's show then how the electrons are distributed in these two sp hybrid orbitals. So now beryllium has two half-filled orbitals that it can use to form two covalent bonds with, in this case, the chlorine atoms. And then we have these unhybridized 2p orbitals here. In this case, they don't do anything, but those unhybridized p orbitals will be important later on. Take a look at the bottom of page 295, and you'll see exactly what we've done here. So we have at the very bottom, in blue are shown atomic orbitals, atomic 2s and 2p orbitals. So one of those 2s, one 2s orbital and one 2p orbital combine to form two new hybrid orbitals shown in green. As mentioned earlier in the notes, one of the lobes, so it shows where the electrons spend most of their time, is bigger than the other. We put those together and we get what we see on the right side. So beryllium has two large lobes that happen to be 180 degrees apart from each other. So question, what is the molecular geometry of BeCl2? It is linear. Now, another question, why is BeCl2 linear? It is linear because the beryllium is sp hybridized, and those hybrid orbitals are 180 degrees apart from one another, giving us the linear structure of BeCl2. Let's try another one. Draw the Lewis structure for BF3. Don't really care about the lone pairs on the fluorines. And go ahead and pause the video if you need to draw the atomic orbitals of boron. So in this molecule, boron forms 3 covalent bonds. In order to form 3 covalent bonds, boron needs to form 3 half-filled orbitals. So question, how many and which of boron's atomic orbitals combine to form, are needed to form 3 new hybrid orbitals? That would be 3. 3 atomic orbitals combined to give rise to 3 hybrid orbitals. It's always an s because there's only one s orbital in the valence shell. So the s orbital combines this time with 2 of the p orbitals to form 3 new hybrid orbitals. Let's draw those. Go ahead and pause after I draw them. They are known as sp2. And again, look at the name. sp2, 2 p's and 1 s combined to give rise to 3 new orbitals. And how are boron's valence electrons arranged in these 3 orbitals? Now boron has 3 half-filled orbitals which it can use to form 3 covalent bonds. Boron has 1 unhybridized 2p orbital, doesn't do anything in this molecule. So let's again go back to the questions I asked about BeCl2. We'll do the same thing for BF3. What is the molecular geometry of boron trifluoride, BF3? It is trigonal planar. Why is boron trifluoride trigonal planar? It is trigonal planar because boron is sp2 hybridized. If you take a look on page 298, we see kind of the same thing as shown here. So you take 1 s orbital, combine it with 2 p orbitals to make 3 new hybrid orbitals. And when they're arranged in boron, they are 120 degrees apart from each other, these lobes, giving rise to a molecule that has a trigonal planar geometry. So that's why it's trigonal planar. Central atom is sp2 hybridized. All right, hopefully you see a pattern here. So go ahead and draw a Lewis structure for carbon tetrafluoride. Draw the atomic orbitals, and then stop there. I'll show you how the atomic. All right, so next up we have carbon tetrafluoride. Go ahead and draw the Lewis structure for carbon tetrafluoride. Draw out the the hybrid. Nope, let's back up. Draw out the orbital diagram for the valence shell of carbon, and then stop there, and then I'll show you how it hybridizes. So carbon has 4 valence electrons. There's its orbital diagram for the valence shell. In order to form this molecule, carbon needs to be able to make 4 half-filled orbitals, so it can make 4 covalent bonds. All right, so how does this happen? In this case, the s orbital is going to combine with all 3 p orbitals to make 4 new hybrid orbitals called sp3. Now, a little note, I have also seen the energy level written before the sp3, so 2 sp3. The previous examples, 2 sp2 and 2 sp. Either way is fine. Just know that in this molecule, the carbon is sp3 hybridized. So again, in order to form 4 covalent bonds, carbon needs 4 half-filled orbitals. In order to form 4 half-filled orbitals, 4 of its atomic orbitals need to combine. 1 s and 3 p's, giving rise to 4 new hybrid orbitals called sp3. Now that carbon has 4 half-filled orbitals, it can use that to form 4 covalent bonds. All right, let's take a look at another one. Very different situation. Oh, going back to CF4, this is on page 301, so you can see the formation of the 4 sp3 hybrid orbitals. Again, some questions. What is the geometry of carbon in CF4? It is tetrahedral. Why is this molecule tetrahedral? It is tetrahedral because carbon is sp3 hybridized. The 4 sp3 hybrid orbitals are 109.5 degrees apart from each other. You can clearly see that on page 301. All right, now let's take a look at something different. We have PF5, phosphorus pentafluoride. Go ahead and draw a Lewis structure. And again, draw the orbital diagram for the valence shell. I'm going to add one more thing to it, though. All right, so take a look at this molecule, Lewis structure. This time we have 5 atoms bonded to the central atom, 5 electron groups on the central atom. In order for the central atom to accommodate 5 electron groups, it needs to form 5 hybrid orbitals, 5 half-filled orbitals. So now notice this time that phosphorus has its valence electrons in the 3rd energy level. Notice too in the Lewis structure that phosphorus has an expanded octet. It goes beyond the octet. So how is it able to have more than an octet? Well, this is where d orbitals come into play. Now, again, notice that the d sublevel, d orbitals start in the 3rd energy level. So an expanded octet is not possible for every atom. It's only possible for those atoms that have their valence electrons in the 3rd energy level or higher, such as the case of phosphorus. Carbon can't have an expanded octet, nitrogen can't, oxygen can't. All of those have their valence electrons in the 2nd energy level, therefore do not have access to d orbitals that are needed to form the necessary hybrid orbitals. So let's take a guess. What is the hybridization of phosphorus in this molecule? Which orbitals, well, let's back up. How many orbitals need to combine to give rise to 5 new hybrid orbitals? The answer is 5. So which 5 atomic orbitals combine to give rise to 5 new hybrid orbitals? 1s, 3p, and 1d. They form 5 new hybrid orbitals called sp3d hybrid orbitals. Let's take a look. So I'm out of room here, so I'm not going to show the unhybridized 3d orbitals. So we get 5 new, they're called sp3d hybrid orbitals, each with 1 electron, allowing phosphorus to form 5 covalent bonds. Let's try another one. Again, same thing, draw a Lewis structure for sulfur hexafluoride. Draw the orbital diagram of the valence shell for sulfur, and pause there. In order to form this molecule, sulfur needs to make 5 covalent bonds. In order to form 5 covalent bonds, sulfur needs, 6 covalent bonds that is. In order to form 6 covalent bonds, sulfur needs to form 6 half-filled orbitals. In order to form 6 half-filled orbitals, how many of its atomic orbitals need to combine? That would be 6. So which orbitals combine to give rise to 6 new hybrid orbitals? 1s, 3p, and 2d orbitals, this time all combined. We get 6 half-filled orbitals, so sulfur has 6 valence electrons, so we get 6 half-filled orbitals allowing sulfur to form 6 covalent bonds with other atoms. And again, just like in the previous example with phosphorus, sulfur has an expanded octet. The only way for that to happen is to have access to d orbitals that can combine with s and p's, in this case to give rise to 6 new hybrid orbitals called sp3d2. What is the geometry around the sulfur in this molecule? It is octahedral. Why is this molecule octahedral? This molecule is octahedral because the central atom, sulfur, is sp3d2 hybridized. Anytime the central atom is sp3d2 hybridized, the electron geometry at the least will be octahedral, 6 electron groups. Going back to our previous example, the only way for the central atom to accommodate 5 electron groups, a trigonal bipyramidal electron geometry, whether that's 5 bonds or 4 bonds and 1 lone pair, doesn't matter. 5 electron groups is to be for the central atom to be sp3d hybridized. So again, see the connection between the VSEPR theory and the valence bond theory. How many electron groups are on the central atom will ultimately determine the hybridization of the central atom, or vice versa. And so all we do is count electron groups in the central atom. That's how many hybrid orbitals we need. That's how many atomic orbitals combine. And you have all of those different possibilities. I forgot to do one. Let's add one more. So maybe underneath number 5, if you have room there, let's draw the Lewis structure for ammonia. And again, draw the orbital diagram for the valence shell for ammonia. Go ahead and pause the video. So take a look at the Lewis structure. What is the electron geometry of nitrogen? The electron geometry is tetrahedral. Its molecular geometry is trigonal pyramidal, but I want the electron group, or electron geometry, tetrahedral, 4 electron groups on the central atom. And according to the Lewis structure, the nitrogen forms 3 covalent bonds, and to do that needs 3 half-filled orbitals. If we look at the orbital diagram, we already have 3 half-filled orbitals. So the question is, does nitrogen form hybrid orbitals in this molecule? And it does. The reason we know this is because the bond angle, the distance between those hydrogens, or those bonds in this molecule, are about 109.5. It's a little less because of the lone pairs. We'll talk about that later. But it's about 109.5, which tells us then that the central atom must form hybrid orbitals. So let's do this. How many electron groups again? That would be 4. In order to accommodate 4 electron groups, we need 4 hybrid orbitals. So in this molecule, nitrogen is sp3 hybridized. Now go ahead and arrange those valence electrons in these 4 hybrid orbitals. Pause the video. So here's what you end up with. So notice that nitrogen has 3 half-filled orbitals. Great, it can use those to form the 3 covalent bonds with hydrogens. And then we have one orbital, one sp3 orbital that's already full. So what are these 2 electrons here? Those 2 electrons there are these ones. The electrons that belong just to nitrogen, the electrons that nitrogen is not sharing, this is the lone pair of electrons. It's in its own orbital. So I just want to show you what happens with lone pairs in the central atom. It's important to note that lone pairs, as well as bonding electrons, will occupy hybrid orbitals. Now, this isn't always the case. Let me give you an example. It says, occasionally molecules form that contain bonds from unhybridized orbitals. One may determine if a molecule contains hybrid orbitals from experimental bond angle data, like in our last example. It has been experimentally determined that the bond angles in NH3 are about 109.5, technically 107.3, but pretty close to 109.5. Let's take a look at this molecule, H2S. Again, let's draw the Lewis structure, and let's draw the orbital diagram for the valence shell for sulfur. Go ahead and pause the video. All right, so here's what we have so far. So now we would, based on what we've seen so far, we would predict that sulfur forms 4 sp3 hybrid orbitals. And it has 2 of those sp3 hybrid orbitals already full of electrons. That's our 2 lone pairs. And then 2 half-filled sp3 hybrid orbitals that it can use to make the covalent bonds. Here's the problem. The bond angle in H2S, this molecule, is about 92 degrees. Now that is not consistent with a molecular geometry of tetrahedral and a hybridization of sp3. So what happens in this case is that the sulfur does not hybridize. It stays with its 3s and 3p atomic orbitals. And then those 2 hydrogens, they form covalent bonds by overlapping their orbitals with the atomic 3p orbitals in sulfur. Now think about this. Where are the 3p orbitals relative to one another? Always, in any p sublevel, where are the p orbitals? They are all 90 degrees apart from each other. They're all perpendicular. And so I'm just going to draw out the two 3p orbitals that are used to make the bonds with hydrogens. So hydrogen's 1s atomic orbital combines or overlaps rather with 3p orbital, two of them to be exact, to form the covalent bond with sulfur. So if you're given experimental data that contradicts what the VB theory says, perhaps that central atom does not hybridize. So be careful with that. If you want to see something a little better than what I drew here, page 308 in your textbooks shows this exact same thing and talks about the fact that sulfur does not form hybrid orbitals when making this molecule H2S. So again, also reference the previous pages and subsequent pages. They do show formation of these hybrid orbitals and how the orbitals between two atoms overlap to form your covalent bonds. Green are hybrid orbitals, blue are atomic orbitals. All right, that concludes this lesson. Thanks for watching.